So here are our two population growth models again, okay, for the population biologists in the room. The red population model here, y equals x. That's an example of a Malthusian model. And the orange, y equals 4x minus x squared. That's an example of a logistic population growth model. And so for each of those models individually, we can say, for the linear equation, what's the slope, what's the intercept, what do those mean? We can ask what are the x-intercepts and y-intercepts of both models. We can find the vertex. By the way, how would I find the vertex of my logistic model here? Right. And what are A, B, and C, by the way, for this? Yes, here's where we want to be careful, right? A is always the coefficient of the quadratic. So even though we write the number 4 first, because it's attached to the x and not the x squared, it's not our A. Instead, what is 4? 4 is our B. That's what's attached to the x. And our A is -1. How about C? 0. We don't have a constant term in this. So if I'm going to find the vertex, I want, again, x equals minus b over 2a. And if b is 4 and a is -1, I'm going to get -4 divided by -2, x equals 2. And sure enough, for the vertex of the parabola we're seeing here, -2 does look like the correct, +2 does look like the correct x coordinate, right? And then we could plug 2 into that equation to find the y. And we'll just trust the graph on this one for now. Y equals 4. Okay, but then the one last thing I want to do is ask, where do these two different models agree? Where do both models predict the same population growth? All right, yeah, so tell me first of all where you see the answer to this question on the graph. What feature of the graph should I be looking for?
0.
All right, so why 0, first of all?
Intercept of zeros.
Okay, right. So when x is equal to 0, in other words, when there's no population at all, both of these models agree there's going to be 0 population growth, which also makes intuitive sense if we're just thinking biologically, right? If there are no organisms, then there's going to be no reproduction, so no growth. Okay, so that's one place where both agree. Is there another place on this graph where both models are predicting the same growth rate? Where x equals 3. So how do you know x equals 3? What's happening on the graphs at that point? The graphs are intersecting one another. What does it look like the y-coordinate is there? Looks like the y-coordinate is also 3. Right. So that's another place that if the population of organisms is 3, whatever our units are, let's say 3,000 units, right? Say I have 3,000 bears or something in my bear preserve, then both my Malthusian growth model and my logistic growth model are going to predict the same growth rate, 3,000 organisms per year or whatever, for that population. Okay, so that's doing it graphically. How would I answer that question? How would I be absolutely sure? Because graphs only ever provide us with approximate answers. We don't know that maybe this isn't like 2.98 comma 3.06 or something like that, right? How could we find that answer analytically? Using the formulas for these models.
Set them equal to each other?
Set them equal to each other, exactly. So that's generally to find intersection points of graphs. We just want to set these two equal to each other. Set equal to each other to find the intersection points. And when you say set equal to each other, what am I really doing here?
Solving for x.
Solving for x, right. So I'm going to take these two places where we see y, and I'm just going to kind of, since those y's are going to be the same, I'm just going to connect them up, right? So my y disappears, and I just end up with x on one side of the equation and 4x minus x squared on the other. And so now I have to solve this equation for x. All right, but how am I going to solve this equation for x? Factor, but I don't want to factor until one side of my equation is 0. So let's make one side of the equation 0. How? subtract the x from both sides. Yeah. That's going to make everything for my left side go away and leave me with a 0. And on the right side, I'm going to get something that now it would be a good time to factor. What's 4x minus x? 3x. And how does 3x minus x squared factor? What common factor do these two terms have?
X.
Yeah, they both have an x. And if I bring out an x, what is its cofactor going to be?
That's 3 and X.
3 from the first term, x from the second term, and a minus. And now I have a factored equation, the other side of which is 0. So what can I do? I can split it apart, just like before, and get two simpler equations. The first is x equals 0, which is already solved. I don't have to do anything. The second is 3 minus x equals 0. And the solution of that is x equals 3. So sure enough, our eyes were not deceiving us here. The two places where these graphs intersect are at the x-coordinates 0 and 3. And if I wanted to know whether the y-coordinate that we saw here was correct, how would I find out the y-coordinate that's associated with x equals 3? Right, plug it into either of the two equations. It's probably easier to plug it into the first one. If I plug x equals 3 into this equation, I'll find that y also equals 3. So sure enough, the point 3, 3 is the other intersection point for these two graphs.